Good morning. My name is Frédéric Parrin, and I'm a JVM runtime engineer at Oracle. And this morning, I will talk about one aspect of Project Valhalla called heap flattening. And I will also describe what will be available with JEP 4.1. So let's start by defining what we mean by heap flattening. In Java today, we can declare a class like this C1 class with fields in field. We can initialize with the content 1 and string field with the content hello. We can instantiate this class. And we can have the illusion that we have created one object, and this object contains the content of our fields. But this is not quite accurate. What we have created is a graph of multiple objects. And the content of those fields are spread across multiple objects in the Java heap. Heap flattening is a technique to avoid partially or totally this distribution of content across the Java heap. The principle is to take the content of the object and to copy it into the instance of the class that declared the field instead of using a reference. So why isn't heap flattening the default? The reason is the identity and the mutability that Java objects have by default. On this example on the left, you can see two instances of class C2 sharing the same content of the class of the field P pointing to the same object point. If the application wants to mutate the object point, the JVM only has one location where it has to make the modification. On the other hand, on the right side, you can see what happens if the JVM had applied heap flattening. The JVM might have created many copies of the initial object, but those copies still semantically represent the same Java object. So any modification to the original object has to be applied to all the copies. This is a very inefficient way to store your identity objects. This is why Project Valhalla has introduced the notion of value classes that are specifically defined to enable heap flattening. Value classes instances have no identity and cannot be mutated, which means the VM can freely copy the content without having to pay the burden to update them. Taking the example of the previous slide and just changing the definition of class point to be a value class, we can see that with heap flattening, we can copy the content in many objects. And if the application needs a new point with a different content, it cannot mutate the original object. It has to create a completely new value. Why would you want heap flattening? There are many answers to that. The first one is memory density. Every object in the Java heap needs a header. And people who are familiar with the Lilliput project know that this is a big burden, big cost in terms of memory. When you flatten a value, the flat value doesn't need a header. It doesn't have to maintain a state about monitors. It doesn't, and the metadata associated with the flat value can be retrieved from the container class. When we allocate objects in the heap, we have a granularity of 8 bytes, meaning if your size of the object is not a multiple of 8 bytes, you might lose some memory, having some waste bits at the end. With heap flattening, the JVM have more opportunity to rearrange the field to have a more compact layout and avoid wasting these bits. The second answer is the GC workload. If you have reduced your memory footprint, you will fill your memory at a slower pace, and your GC will trigger less often. Flattening also reduces the number of objects that the GC has to manage. When a GC is in marking phase, every time it processes an object, it has to find if this object has object reference in it. And to do that, it has to go to the metadata, the instance class describing the object, and find a data structure called the hook map. And there is a couple of directions to find this information. This is a cost that JC have to pay for every single object. With flattening, there is less object, and the flattened value that contain object references have this information included in the hoop map of the object in which they have been flattened. So let's see what are the effects on an example. So here a class node, which might look weird because you have integer val, and why not using int type for this field? Just think about what the class could be: a generic class, node of t, and we have generic specialization and t equals integer. And if you apply generic specialization, we'll end up with something very similar to this one. The simple program creates a binary tree of 40 million nodes of this class and bounds it once, incrementing the val field for each node. One thing to know is that integer is one of the JDK migrated classes. Today, it's a value-based class, but if you are running the JEP for one preview VM, this class will automatically become a value type and will be optimized by the VM. So what would be the impact of heap flattening? You can see the number on the top here. On the left, you have a run without heap flattening, and you have a total execution time of 4.5 seconds. On the right side, with heap flattening, the execution time is down to 2 seconds. Below that, you have an output from the perf profiler. It just shows what threads were consuming the most CPU during the run. On the left side, you can see that the most active threads were the GC threads. And at the bottom, you can see the Java thread, the one running the user code. On the right side, you can see this Java thread doing exactly the same work. He's the one that is consuming proportionally the most CPU. The other GC threads are just below this one because they have less work to do. The third answer is cache efficiency. If you have an array of references, the elements of your arrays are spread across the heap. If you flatten the array, now your elements are stored contiguously in memory. You have a better cache efficiency because you have a better spatial locality when iterating over your array. In some cases, combining this flattening and the C2 optimization rascalization, we can achieve performance for flat arrays that are similar to the primitive arrays. Heap flattening can provide significant performance gains, both in terms of memory and CPU workload. But access patterns matter. Flat arrays provide a better cache efficiency when you are accessing them sequentially. If you are performing random accesses, like when you are sorting an array, you won't benefit from this spatial locality. There are also some additional costs associated with heap flattening. The interpreter, the runtime, the C1 compiler are not designed to operate directly on flat values. They have to create a standalone copy in the heap, what we call heap buffering, before being able to operate on them. It's a trade-off we made to privilege the peak performance in the steady state of the application when everything is running with C2 compiled code. So what kind of heap flattening to expect with JEP for one? One thing you might notice if you have been following the Valhalla project is that the JEP for one value class are slightly different than the previous models. Original value types had no identity, were immutable, were non-atomic and non-nullable. In JEP for one, they still have no identity and still immutable, but they are now always atomic and they are nullable. Those changes come from our better understanding of value types and we were iterating over different models. But those changes create new challenges for the VM and force us to some trade-off. Let's start with non-atomicity. And people are often confused. Why are we speaking about atomicity with immutable values? The answer is that you can store an immutable value into a mutable container. It could be an identity object on an array. and you can change the content of the field. Non-atomicity means the possibility to see some partially outdated data. And you have an example on the right here. You have an object with a flat value made of two fields, x and y. The original value is 0, 0. A thread T1 starts to update this flat value, but doesn't do it atomically. It starts by writing the x field, changing the value from 0 to 4. Then another thread running concurrently, thread T2, reads this flat value. It reads the x field, find 4, reads the x field, find 0. And finally, the thread T1 completes the update by writing the field y with content 2. The original value was 0, 0. The new value is 4, 2. But thread T2 has been able to observe the value 4, 0 that should have never existed. Something important to notice is that this problem only happens when you have concurrent accesses. If your application is monothreaded, or if you have other mechanisms to prevent concurrent access, you will never see this kind of value tearing. However, without having to guarantee atomicity, C2 can perform much better optimization. It doesn't have to consider the flat value as a single entity, but it can decompose it and see I, x, and y are two completely independent variables. The challenge here is that specifying the behavior and the limits of non-atomic values in the Java memory model is very, very hard. And there is a very fine balance to find between providing enough flexibility to the VM to perform optimization and provide a user model that provides enough guarantees that developers can think about their code. So this one is still a work in progress. So for JEP 4.1, we have a temporary solution that is making all value types always atomic, which means there will be no semantic difference between flat and non-flat values. Atomicity of flat values have a cost. If C2 has a scalarized value, it means it deconstructed this value in its component. It has to reconstruct a local copy of this value with the right format before updating a container. In the reverse, when reading, C2 has to read the whole value before deconstructing it, extract the different fields. Reads and writes must be atomic. We have been exploring many solutions at the beginning of this project to see how to achieve that. We try monitor spin logs, system logs, transactional memory. At the end, with the current state of technologies, we only have two solutions providing acceptable performance. One is to use an indirection, which means no flattening. And the other one is to use the naturally atomic operation of the HotSpot platform. On most platforms today, these atomic operations cannot handle data bigger than 64 bits. So in JEP 4.1, you won't see anything bigger than 64 bits being flattened. This limitation can be lifted as CPU provide better atomic operations. Atomic operations require correctly aligned data, which has an impact on layouts. You can see here on the bottom a layout on an object with two 5 bytes values, one green, one brown. We could have a very compact layout, packing everything as close as possible. But then we cannot use atomic operation to update them. Because of these constraints, the VM has to generate the layout on the right, and it had to add some padding in the layout. The other change is about nullability. Original value types were always null-free. But we realize that nullability is concept much broader than value type, and we should not have one mechanism specifically for value types. We need something that is applicable to any type. So linking value types and nullability was not a good choice. So the null restriction is a different JEP that is in progress and that will be delivered later. So in JEP 4.1, values are always nullable, which means that we require one more bit of information to store the nullness status. In HotSpot, This bit of information is rounded up to 1 byte for implementation reason, and I will come back to this point later in this presentation. This byte is automatically added to the value type by the JVM. The null marker must be updated atomically with the rest of the value. We try many protocols to try to separate the null marker and the value to be more efficient in terms of memory, and it simply doesn't work. There is still a way for the possibility to observe a transient value or to resurrect an obsolete value. So the whole value and the null marker have to be treated as a single atomic unit. When the new restriction JEP is delivered, flattening policy in the JVM will be updated to provide better flattening of non-null value, non-restricted value types. So the heap flattening implementation in HotSpot. In JEP 4.1 preview, HotSpot will automatically try to flatten all fields with concrete value class types and all arrays with a concrete value class element type. But in order to be able to flatten something, you need to know the layout of this thing. You need to preload the value classes before computing the layout of the container. With JEP 4.1, when you are using JavaC with the enable preview flag, JavaC will add a new attribute in the class file called the loadable descriptor. JVMs are allowed to try to preload the classes listed in this attribute in order to have more information to perform layout optimizations. We have a special handling of the JDK migrated classes, so you don't have to put them in this class. And even if your class file are lacking the loadable descriptor attribute, the JVM will be able to flatten those classes. This is only during the preview period. It is recommended to recompile the classes if you are using value types. Not only you need to recompile the classes using the value types, but after the preview period, everybody will have this attribute in the class files. When computing layout of flat values, maximum memory density is not the only goal. In an example here on the upper right, I have a class with 3 fields, an int, a short, and a 5 bytes value. You can see the layout here. You have the int 4 bytes. You have the value with 6 bytes because we have to have a null marker in it, and you have the short. And the value is correctly aligned for atomic operations. We achieve maximum memory density. But what happens if we try to update the value? The atomic operations come with predetermined sizes, 8, 16, 32, 64 bits. Because of its size, the value is updated using a 64-bit atomic operation, and there is a risk to overwrite the value of the short field. We could prevent that, for instance, by using a compare and swap operation to ensure there is no concurrent write to the short field while updating the value. But compare and swap are very expensive operations. So in this case, HotSpot will compute a less efficient layout, putting padding at the end of the value just to have a reasonable access cost to this value. Not the best memory layout, but still better than an indirection and a header. Identity classes have a unique layout. In their metadata, there is one description that is used for all instances of this class. A single layout would be inefficient for flat values. We have seen in the previous slides that atomicity and nullability increase the memory footprint and the access costs. If users give up these properties, they should not have to pay this cost. As an example, if I have a class point, a value class point with 2 fields, short fields, and create an array of it, the layout of the default nullable array of point has an element size of 8. I need 4 bytes to store the content of the field, 1 byte for the null marker, and I have 3 bytes of padding because I have to take into account the size of the atomic operation. But if the user gives up on nullability, he or she is right to expect to have a 4 bytes element size, basically there's no point paying cost for a feature it doesn't use. The way we are doing that is by supporting multiple layout variations. HotSpot can compute several layouts for a given value class based on semantic requirements. Those semantic today being nullable or not, atomic or not. There is an initial field layout computed based on the value class itself. Its field, the class, the property of the class, and the hardware capabilities. The field ordering will remain consistent across all layouts, which is important to be able to quickly copy content from one layout to the other. Variations of this layout are derived by modifying the alignment constraints for atomicity and the size to take into account the optional null marker. When flattening a value, HotSpot will select the most efficient layout satisfying the expected semantic at the use site. At the bottom of this slide, you can see the dump of the layout of an identity class with 3 fields. They all have the same type value, but each one is using a different layout. The one at the bottom is a non-flat field, is using reference. The 2 other ones are flat. The number you can see on the left, 4/4, 3/1, represent the size of the flat value and its alignment constraint. Value types are an open type system. User can define value types with any shape and any size. Each layout may require specific access codes. This is a set of the instructions we are using to read and write those values. And we need to support that in all field accesses and array accesses. And each component of the VM has to implement them. The interpreter, the runtime, GNI, C1, C2, sometimes these things involve unsafe, bundle, all have to adapt to those new layouts. The selection of the layout depends on many parameters, and some of them are outside of the Java type system, like nullability or atomicity, which create new challenges for arrays because of array Java covariance. If a method receives an object array argument, there is no way to deduce from this Java static type what will be the layout of the array the method will receive at runtime. If the Java static type system doesn't help, we will have to base our optimization on profiling. Going back to this 1 byte null marker, why are we wasting so much memory to encode null? We could reuse some spare bits like the one that are in Boolean, which have 7 unused bits. The 1 byte null marker is only the beginning. It's an universal solution that works for all value types, even the ones without any spare bits or unused patterns. And it is relatively simple to implement. And I'm emphasizing relatively because we had a lot of work. We did a lot of work just to support this one. We had a lot of implicit null check, for instance, just relying on protection of the first page of the process to detect null pointers and delegating all the null pointer handling to the signal handler. All those implicit null checks now have to be explicit. We have to check if the value has a null marker, where is it, and we have to test it. We can also combine null markers with existing Java type to reuse the spare bits or the unused patterns. But this complexifies the handling of this type, because now you have to filter out this null marker when you need to use the value, or you have to preserve or restore the null marker when you are writing a new value. And there is a complexity budget that the VM can handle. We cannot imagine adding new encoding of null every week. It won't scale. We are considering such more efficient encoding. And I put here, for reference, a proposal from John. We're using some unused patterns in OOPS and object references. JEP 4.1 is only the beginning of the journey for heap flattening. We are putting the foundation for further optimization. The evolution of the Java language, especially providing the way to express null restriction on non-atomicity, will unlock more optimization for the JVM. We still have more flattening optimization in mind, and sometimes prototype, and even more JIT optimizations for flat values. We cannot implement everything at once, so we will deliver that incrementally. Our flattening policies can be adjusted. Today, they are only based on type and properties. Users don't have any way to communicate the access patterns they will have of the data structure. A highly mutated data structure and another data structure which is almost never updated might deserve very different flattening decisions. We're going to have an early access of JEP 4.1 this fall, and we're working on having a JEP 4.1 preview. So please go try it, provide feedback, and don't forget to compile with Nullable preview. Thank you.
Thank you. One of the last points you made on the last question was about access patterns. And are you thinking about putting, say, JFR-like events into the VM so you can profile access patterns to give hints to the users about what they may do to tell later on? Because I think dynamically changing the flat layouts as you go is going to be harder than just telling the users the access patterns and then adding extra information to the value classes or how to control the access patterns through some form of declarative description.
The first step would be to allow users to explicitly specify what are the access patterns they envisage. Profiling would be a very useful tool for users. However, we cannot change layouts dynamically. This is a strong limitation we have. So we will have to have some training runs or to collect data during runs and use this information about access patterns in the next run. So this is something we can work on, yes.
You can flatten a point 2D class. Could you also flatten a point interface if it was sealed?
No, the reason is we can only flatten something that is monomorphic, that on single layout. So interfaces and abstract classes are not flattened because they are polymorphic.
Gotcha, and that goes even if the polymorphism is bounded.
Yes, we have no plan to try to flatten something polymorphic. It has too many. It's too complex.
So you mentioned that C1 and interpreter cannot work with these flattened values, and there is this heap buffering thing. Can you elaborate how this works, especially if there exists C2 code that works on the same objects and C1 code?
So if you have a flat field, C1 and interpreter just work on references. So they cannot do anything, they cannot see a flat value and try to do something, invoke a method, or extract from the field directly. They will allocate an instance of the type of the value class in heap, copy the content, and then they will operate on it like any regular object. C2 has the capabilities of extracting the information directly from the flat value without allocating anything in heap, and is able to invoke methods, extract fields, without having to reconstruct the value. There are a lot of optimization and modification in C2 to do that, but this is where we are getting a lot of our optimizations.
Wait, does this mean that we have simultaneously a pointer to a heap value and a flattened copy of it in the object?
There are some cases we have to have both. When you have C2 code coding C2 code, we don't have to do that. When you have a mix and match of C1 compiled code, C2 compiled code, or interpreter code and C2 compiled code, we have to maintain both.
C2 already has the ability to do escape analysis, which means scalarizing objects outside of the heap. So every value object is an immediate and perpetual candidate for scalarization. That's why it works. And but you can have residual pointers to buffered value objects simply because the use point at that place might be polymorphic. In other words, the compiler doesn't know statically what the type is. It could be just an object variable, and yet there's a value type in it. And right next to it, there's a fully typed variable of the same value type. That one can be flattened, but the one that's of type object will not be flattened.
So this may be a bit of a naive question because my memory of the Java memory model is not so strong. But you talked a bit about tearing and non-atomicity. I understand how that matters when I have bugs, race conditions in my code. How much does it matter when I have a correctly locked program?
The challenge is to allow some form of tiering that people can understand where are the limits of tiering, while not having to pay any cost when you have a correctly synchronized program. And this is a hard part. We could say, here an option, and you can declare your variable class being completely non-atomic. And your program is correctly synchronized, everything is fine, but people with concurrent accesses will be in hell because they won't understand anything. So we have to find the balance between having no cost at all when you have a correctly synchronized program, but still having some reasonable guarantees when you are doing these concurrent accesses. Okay, thank you very much.